You're looking at a diode. Seriously, you'll find these things in pretty much every electronic device you own. And, in our textbooks, it's always this simple, perfect one-way gate for electricity. But what's really going on inside when it gets put to work? Well, today, we're going way beyond that simple model to uncover the fascinating and, honestly, kind of messy physics of a real-world PN diode.
See, the ideal diode we learn about is this perfect one-way street. Current flows forward, and absolutely nothing flows backward. It's clean, it's simple. But the real world? Well, it's a lot more interesting. A real diode has delays, it loses energy, and its behavior is driven by some surprisingly complex physics going on under the hood.
All right, so here's how we're going to tackle this. First, we'll set the stage, the ideal versus the real. Then, we're going to dive deep into the inner life of the charges themselves. From there, we'll see how that helps us build a real-world model for current. And then we'll get to the really surprising part. What happens when you try to switch a diode off? Finally, we'll see why all of this really matters for engineers.
So let's start with the big question. We know a diode is just a junction between two types of semiconductor material. So what is happening right there at that junction that keeps it from being a perfect, instantaneous switch? What's the holdup?
To get the answer, we have to zoom in. Way in, down to the level of the semiconductor itself. The story of a diode isn't about the device. It's really the story of its charge carriers, the electrons and their funky counterparts, the holes. Everything that happens is because of how they move.
And the master rule that governs all their movement is called the continuity equation. The easiest way to think about it is like a super strict accounting law for charges. It basically says that for any little piece of the semiconductor, the number of electrons or holes inside can only change if they flow in or out, or if they're created or destroyed right there on the spot.
And that brings up a really weird question, right? How can a charged carrier, like an electron, just vanish? Well, the answer is a process called recombination. A free electron finds a hole, it falls in, and boom! The two of them basically annihilate each other, releasing a little puff of energy.
Now, in a perfectly pure silicon crystal, this doesn't happen very often. But real-world crystals, they have tiny flaws, little imperfections, and these defects act like convenient meeting spots for charges. The main way this happens is through something called Shockley-Read-Hall recombination, where these imperfections create traps. Think of them as little energy stepping stones that make it way easier for an electron and a hole to find each other.
So here's the play-by-play. First, one of these defects, a trap, snags a wandering electron. This trap is now negatively charged, so it attracts a positive hole. Once the hole gets there, they recombine, and poof, both charge carriers are gone. It's a clever, indirect, two-step dance.
So that's the most common way charges disappear. But what if you really crowd the semiconductor with charges, a condition we call high injection? Well, then a more chaotic process can take over. It's called Auger Recombination, and it's a three-particle mess. Basically, an electron and a hole recombine, but instead of releasing light or heat, they transfer all that energy to a third carrier, kicking it way out into the crystal.
Okay, so we've established that charges can just disappear. Now let's look at how that one simple fact completely changes how we model the current flow. It turns out that because of recombination, the physical size and shape of the diode suddenly become incredibly important.
And this leads us to a really key distinction. It all boils down to one question. Are the charge carriers more likely to recombine before they reach the other end, or will they make it all the way across? This is what separates diodes into two camps, long base and short base. In a long base diode, the regions are so wide that most of the carriers recombine before they can escape. But in a short base diode, the regions are really narrow, so most of them make it to the other side.
And because the underlying physics is different, the math has to be different too. It leads to totally different equations for the diode's current. For those long base diodes, the key variable is something called the diffusion length, which is basically how far a carrier can wander before it recombines. For short base diodes, it's much simpler. It's just the physical width of the region.
All right, and now we've arrived at the climax of the story. All of this physics we've talked about, the injection of carriers, their limited lifetime, recombination, it all comes together to create a huge practical problem when we try to turn the diode off. It doesn't just stop.
So what really happens when you try to switch off a diode that's conducting? You'd think the current just drops to zero, right? Nope, it actually reverses direction. For a brief but critical moment, the diode conducts backward. Why? Because all that stored charge we pushed into it has to get swept back out. Only after that reverse recovery period is the diode finally, truly off. And in this delay, this reverse recovery time, it's not just some theoretical blip on a graph. It's a real, measurable thing. In a numerical example from the source material for a high-powered diode, this delay can be as long as 42 microseconds. Now that might sound incredibly fast, but in the world of modern electronics, that's an eternity.
So here's the crucial point. Why on earth does a delay measured in millions of a second matter so much? Because in power electronics, where we are switching currents thousands or even millions of times per second, this tiny lag has absolutely enormous consequences.
Every single time that diode goes through its reverse recovery, it's basically acting like a momentary short circuit, and that generates a burst of heat. This wasted heat kills the efficiency of the whole system. It limits how fast you can switch things, and the abrupt current spikes can create electromagnetic noise that messes with other components. For designers, it's a massive headache.
And this all leads to a fundamental compromise right at the heart of semiconductor design. It's a point that was captured perfectly in the university lectures this entire explainer is based on.
Here's the core idea. If I want a diode with a high breakdown voltage, I have to accept slow switching transients. And there it is, the essential engineering trade-off. To build a tough diode, one that can handle really high voltages, you need to make its internal region wide. But that same wide region stores a lot of charge, which makes it a slow diode with a long recovery time. You can have tough, or you can have fast, but you can't have both. And that single, fundamental conflict is what continues to drive so much innovation in power electronics to this very day.